An object moving in a circle is constantly changing its direction. Therefore, it must always be accelerating. Figure 6.8 shows the path of an object moving in a uniform circular motion. If we take different points along this circular path and compare how the velocities at those points are changing, we will see the change in velocity is always towards the center of the circle. Centripetal is a word that literally means toward the center. So we can call the acceleration of an object moving in a circular motion centripetal acceleration. Let's take an object moving at an orbital velocity of v around a curve of radius r. As it moves, it sweeps out an angle, theta, and travels some distance along the circle, s, in a certain amount of time, t. Its orbital velocity has not changed. The magnitude is still v, no matter where on the path it is. But the direction is changing. This is the acceleration we are trying to determine. Now we know that the ratio of the arc length to the radius is equal to the angle in radians. We also know that the orbital velocity is the change in the arc length divided by the time. Remember, velocity is a vector, and we can add vectors. If we take the velocity vector at our start point and add it to our velocity vector at the end point, we can determine the change in velocity over the course of our arc. The triangle that this vector addition forms is similar to the triangle formed by the radius and the arc length of our path. If we take the ratio of change in velocity to the velocity, we can then set that equal to the change in arc length over the radius because of those similar triangles. Since we are trying to determine the acceleration, we can algebra our way into finding a change in velocity over time. We can do this by multiplying on both sides by v and dividing by change in time on both sides. Notice on the left, we now have a change in velocity over change in time, which was our original definition of acceleration. Change in velocity over change in time is acceleration. We are going to designate that this is acceleration in a circular motion by giving the a sub c. So a sub c just simply means centripetal acceleration. And we determined a while back that the change in arc length over change in time is the velocity. This means then that the centripetal acceleration is equal to the orbital velocity squared divided by the radius. So increasing the velocity greatly increases the acceleration. Decreasing the radius also increases the acceleration. We can also express this in terms of angular velocity by substituting velocity equals omega r in for the velocity. So centripetal acceleration can be written as either the orbital velocity squared divided by the radius, or the angular velocity times the radius. Remember that in order for an object to accelerate, there must be an outside force acting on it. When we have an object moving in a circular motion, we refer to this force as centripetal force. And as with acceleration, the centripetal force is always towards the center of the circle. Newton's second law tells us that force is equal to the mass times the acceleration. So Fc equals mac. Again, we can designate with a subscript c to show that it is referring to circular motion. For centripetal force, we will use the centripetal acceleration. So we can write this expression in two ways, one using the orbital velocity and one using the angular velocity. So what is the magnitude of the centripetal acceleration of a car following a curve of radius 500 meters at a speed of 25 meters per second? We are given the velocity and the radius, so we can use our centripetal acceleration equation to solve for the acceleration of the car. We end up with 1.25 meters per second squared. Now, a curve with a radius of 500 meters is pretty gentle turn, even when there is being driven at a high rate of speed. If we compare this to the force of gravity, we get a ratio of 0.128. Definitely something you would notice, but not something that would overwhelm you. So let's calculate the centripetal acceleration of a point 7.5 centimeters from the axis of a centrifuge spinning at 7.5 times 10 to the fourth revolutions per minute. Since we are given the velocity in revolutions per minute as opposed to meters per second, we need to convert that into a change in rotation angle and find the angular velocity. Now remember that angular velocity is recorded in radians per second. Also remember that one revolution is equal to 2 pi radians. To convert the 7.5 times 10 to the fourth revolutions to radians, we need to multiply by 2 pi. Since it is most common to record angular velocity in radians per second, we want to convert the minute portion of that label to seconds. After all the conversions, we find an angular velocity of 7,854 radians per second. While we're thinking about those conversions, we need to convert our centimeters into meters. Then we can use our centripetal acceleration equation to find 4.63 times 10 to the sixth meters per second squared. You might notice that the labels of our problem include radians, but our answer does not. Remember that radians are unitless, so when we get to the end of a problem that includes that label, we can just ignore it.